So what we derived in the previous slide, a e raised to minus I by h cross et minus px, is a sort of simplified version of the actual expression psi of x comma t. But again, firstly we don't know the a value there, so we cannot say we have properly derived the wave function. And like we already saw, we are not going to do that either. That is not the point of this discussion. So what we started out saying was, given one quantity and knowing the wave function, I want to be able to derive the other quantity. So that is what we are going to look at now. So we'll be looking at two cases, time independent first and then time dependent. So what does the time independent case mean? In cases where E is constant and potential energy V is independent of space and time. The momentum is also constant, independent of space and time. What does this mean? So we're going to talk about cases where the total energy is constant and the potential energy is also independent of space and time. Independent of space and time means constant. So we know that total energy is equal to potential energy plus kinetic energy. They're telling us total energy is constant, potential energy is also constant. Meaning obviously the kinetic energy also has to be constant, right? And if the kinetic energy is constant, then the momentum is also constant. Why? Because kinetic energy is half mv square by 2. You multiply both the numerator and denominator by m, you will get m squared v squared by 2m, right? And momentum we know is mv. So this m squared v squared by 2m is basically p squared upon 2m. So your kinetic energy and potential are related to each other. Momentum are related to each other. Kinetic energy is mv squared by 2 into m by m. So is what you get p squared by 2m. So if your kinetic energy is constant, then your momentum is also going to be constant and vice versa. So if my total energy is constant and potential energy is constant, then my kinetic energy is obviously constant because of law of conservation of energy. And if my kinetic energy is constant, then my momentum is also going to be constant, independent of space and time. And in such a situation, I will apply the time independent Schrodinger's equation to derive whatever quantity I want to derive. So that tells us when we use the time independent equation. Now we'll actually go ahead and derive that equation. So this equation in the yellow box is what we derived at the end of the previous slide. So now this is in terms of x and t, and we just saw that all the quantities we are dealing with here, total energy, potential energy, kinetic energy, momentum, and of course mass, everything is independent of time. So the time element here is it is basically constant, right? So you have some a e to the power something something t, and that is basically constant. Nothing is changing with respect to time. So we split this equation, which is in terms of x and t, into an equation in terms of x and an equation in terms of t. And then we consider this as a constant, meaning we are not going to do anything about this part. So how do we split? A e to the power ipx upon h cross, and this one becomes e to the power minus iet by h cross. So basically this is a product of two terms, right? A e raised to minus iet upon h cross and a e raised to ipx upon h cross. This minus and minus they cancel each other and become a plus. So this is basically a product of two terms, and those two terms are what we are taking. The one which is in terms of x, we are calling it psi of x. The one which is in terms of t, we are calling it phi of t. And because this situation we are dealing with is independent of time, we will be ignoring this entire psi of t expression for this situation. So we will just treat that as a constant and we will equate it to 1, let's say, for example. So we will only be going ahead with this part of the equation. And why is it valid? Because nothing changes with respect to time. So the existence or absence of the second function psi of t makes no difference. So we take this expression we have, psi of x equals a e raised to ipx by h cross, and we go ahead with it. Now you differentiate with respect to x, you will get ip by h cross times a e ipx by h cross, which is nothing but ip by h cross times the original function itself. So you take this function and you differentiate it, you will get ip by h cross times the same function. So this is what we have now. We took a function, we differentiated it, we got some ip by h cross times the same function. Now you take this ip by h cross to the opposite side. You take I by h cross to the opposite side because I and h cross are constants. P is a variable, let P remain here. You get h cross by I times the derivative of a function is nothing but P times the function itself. So this is an important thing to observe. You're taking a function, you're differentiating it and multiplying it by a constant. It gives you back some other quantity times the original function itself. So this is what we mean by eigenfunctions and eigenvalues. So this is similar to the eigenvalues and eigenvectors you will learn in linear algebra, but there you will learn in terms of matrices and this is in terms of functions. So there is a similarity, a mathematical proof about why this is equivalent to that, but that is obviously beyond the scope of this course, so I am not going to go into this. So for the purposes of this lecture and this subject, this course, you understand that you have a function, you perform some operation on that function, you get back some quantity times the same function, then the function is called the eigenfunction, this quantity is called the eigenvalue, and whatever operation you performed is called the operator. So here my operation is you differentiate the function with respect to x and then multiply with h cross by I, and the function I am using is the wave function psi of x, where psi of x is a e raised to ipx by h cross, and the result I am getting is p times my same function. So p is my eigenvalue, where p is the momentum. So this is what we have derived so far. We basically took the function we derived in the previous slide, we split it into two parts, one in terms of x, one in terms of t. We are discarding the t part because this entire situation is independent of time, and we differentiated the x part, we did some shuffling of the numerator denominator, and what have we learnt, that when you take this function and apply this operation, you get back p times this function. So this p is the eigenvalue and the corresponding operator is h cross by I times dou by dou x.